Today, I'm going to talk about several different topics. Just about everything I'm talking about today is very much in the news, very much the last few months, even last few weeks of going on. And these are all unsettled topics. So it's going to be a little bit disorienting at times. I don't have something that was developed over 2 centuries and so on. Just trying to report on things are relevant right now, and some of the things, maybe a lot of the things, are even going to be wrong. But I'm just going to report where we stand right now. Supermassive black holes and galaxies. We have touched on that. I'm going to talk about a little bit more. Talked about the very first galaxies formed in the universe. Then after the break, I'll talk about pulsar timing array. Later, Hawking radiation and wormholes. Now, people have asked me about these topics, so I've added them in, but they're pretty far out, some of them.
Yeah. Roger, do you mind clicking OK to get rid of that?
Okay. Tell me again how this okay, right? Okay. And does that do it?
Yeah, that's it.
All right. Now, pardon me?
Yeah, it's okay because it's going to come back onto YouTube and don't worry about it.
All right. We've talked a little bit about that galaxies contain black holes. This was something completely unexpected, although that's not entirely new right now. And for example, our galaxy, the Milky Way, has a big, massive, what we call supermassive black hole, about 4 million times the mass of the sun in its center. Andromeda, our near galaxy, has 100 million solar mass. Okay? They vary a lot, but it looks like just about, and maybe all, galaxies have a black hole in the center. So, and they can be very big. And so this IC 101 may be 40 to 100 billion solar mass. Here is one of the record holder, we think, Phoenix A, very distant galaxy, 8.6 billion light years away, and it may have a black hole, and there's different estimates now between 30 and 100 billion solar masses. The question is, how do they get that big? I mean, they do eat stars, eat massive stuff, but this is a lot of mass. And it's very difficult to understand how they can grow to this size. And here's a comparison of the sizes. You probably can't read it. This is the size of Pluto's orbit, so the size of our solar system. And this is the black hole of Ton 618. And Phoenix 8 has this black hole. So it's just unbelievable. And remember, these black holes are very compact things. If the sun became a black hole, it'd be just 6 kilometers in diameter. 6 kilometers. This is this big. Gosh. And here's a few more. 3 million suns, 20 million suns, 200 million suns. This one here, billion suns. So no, that only took those 2 that I showed. Okay. These probably those pictures.
On the right.
On the right, yeah. So a big question is, what is their role in the evolution of galaxies? Some of them are very active when they become quasars. Some, like the one in our Milky Way, are inactive. They're big black holes, but they're not doing much. Others are doing an awful lot. Yeah,
The percentage of black holes as they get larger, in relation to the timeline to the Big Bang.
well, that's something we're trying to figure out. What I'll show shortly is that there are big black holes very, very early in the Big Bang. And there's not a simple time thing. Can't say they get bigger as the universe is getting older. It's much more complicated than that. And Andromeda and the Milky Way are just about the same, must be just about the same age, but they have very different black holes. Well, one way that things might happen is that we know that galaxies collide pretty frequently. And one way that this could happen, here's one of these connections, is that these two black during a galaxy collision like this might merge. Like we've seen the small mergers, this could be an effect. And that would be one way for galaxies to, for black holes to grow. And see, the merging phenomena is not unusual. And you can see
Are
here.
these real pictures or models?
Those are real pictures. They're really good doing this. And they get very distorted then from the gravitation. Interestingly, we're in, wait a minute. Okay, I went ahead of myself. Here is one case where we are seeing something like that happen. This is called OJ 287. It's a very, very active galaxy. And furthermore, the galaxy, it's been known for 100 years that every 10 or 12 years or so, it gets brighter briefly, and it gets fainter again. Well, what's now been determined is that this OJ 287 has two black holes very close to each other. Two, probably from a collision. One is about, I think I have it in the next slide. I think it's about 100 million solar masses. Let me take that. Oh, okay, so I'll explain everything.
$3.5 billion light years away from the Earth, in the galaxy OJ 287, supermassive black holes are locked in an explosive dance. Position of the supermassive black hole here is 18 billion times more massive than our sun. And with this incredible mass, it commands an enormous accretion disk, and it slings its companion black hole with a mass of 150 million solar masses around with ease. As the small black hole flies around the central monster, it plunges through the accretion disk, creating super Eddington flares, which are brighter than 1 trillion suns, and this occurs twice every 12 years. Although astronomers have studied this explosive dance for 130 years, understanding the motion of these black holes and the timing of flares is challenging. In this extreme gravitational environment of these two supermassive black holes, calculating orbits becomes far more difficult than calculating orbits of, say, the Earth and Moon. Properties such as the mass and spin of the two black holes is needed to roughly understand the orbits. But to accurately predict the orbits, normally subtle aspects of how space is bent must be included. As the smaller black hole runs around its partner, it will send out ripples in the fabric of space, known as gravitational waves. It may seem insignificant, but accounting for the nanohertz gravitational wave changes the prediction of when the black hole runs into the accretion disk and launches flares by 1.5 days. Similarly, the exact shape of each black hole matters. If the black holes aren't perfect spheres and don't obey the no-hair theorem, the predictions of the flare times will also be wrong. Armed with a detailed orbital model, astronomers predicted the flare caused by the smaller black hole plunging through the accretion disk would occur on the 31st of July 2019. The trouble was the galaxy OJ 287 would be obscured from the Earth by the sun. Luckily, the Spitzer Space Telescope could watch this flare from its vantage point 254 million kilometers away from the Earth. Comparing against data from a similar flare in 2007, the Spitzer observations revealed that the prediction was accurate to within 4 hours. This remarkable result showed that black holes are indeed spherical, to an error within 15%. With this triumph, astronomers will push our understanding of physics even further than explosive elements. It may be that in the near future, we'll be able to see this collision take place with the Event Horizon Telescope. How incredible would that be to see an event that astronomers have studied for over a century?
Cool, isn't it? I've heard that some people are thinking that actual merger could happen in as little as 10,000 years. Cool.
Earliest one.
Why did I end up here again?
Click on this line.
Oh, okay, yeah. Well, through careful observations. This is observational work. And as you can see, it's combined with theory too, as he described, that try to calculate it, a theory that we believe, and cool. I actually observed this object about 50 years ago when I was a grad student, but didn't get anywhere with it. Here's one where we have 3 interacting black holes. These are not as close. They're about 74,000 and 318,000 light years apart, but they look like they're 3 interacting black holes. So the idea that black holes evolve through collisions with other black holes, through galactic collisions, seems to really be working. But we have a lot of work to do to understand it. Interesting thing is we're about to collide ourselves with Andromeda. And this Andromeda is our nearest neighbor galaxy. And see if we can do something here. And here's a simulation of what that collision looks like. Not too imminent. Really big things that's going to happen in about 4 billion years. But we are on the path. Keep remembering this procedure here. Here's what it'll look like from the, if anybody's left 4 billion years from now, this is what it's going to look like. You're standing here looking out. And now this is space movie. That is it. Uh, Then the combined galaxy will be a giant elliptical like M87 is.
two black holes, influence the
Well, you'd like to explain how that would work?
Yes, so.
Okay, well, as you can tell, this is a subject for research. We have not seen directly. I'll talk about some indirect measurements of collisions of these supermassive black holes, but it's very likely they occur, and that's something that we're looking for. But in the sense of also talking about what's going to happen in the future, just thought I'd describe this amazing telescope, which just had its first light about a year ago, and they're just now in the process of observing. The idea of this telescope is called the Vera C. Rubin telescope. It's in Chile, near the Atacama Desert. The idea of this telescope is going to observe the whole sky that's accessible from the southern hemisphere every 4 days, and take a picture of billions of things every 4 days, and then see how things change. And see, for example, OJ287, big galaxy, big black holes, big everything, it was seen to change. So one of the things we want to see in the universe is how do things change? That's how pulsars were discovered too, when Hewish and Bell had this radio telescope that was designed to look for changes. That's the, and this is just opened. And just to give you an idea, the field of view, each picture it takes is as big as this compared to the moon. So it takes pictures of billions of things. This is the field of view of the JWST. It's actually a little bit smaller. I couldn't get the things. But see, the JWST is designed to look for very, very faint objects in a small field of view. This is also looking for faint objects, but not as faint as the JWST, and it's also a ground-based telescope. But it looks at a huge field, so it looks at lots of objects. An optical telescope. It works up to the near infrared to about 1 micron, but it's a ground-based optical telescope. And here is one more of these. And this is pretty spectacular. This is the Virgo cluster. We're a member of this cluster. And this is one of the first pictures that it took. And look at what it's seeing. Thousands of stars, galaxies, everything.
Are most of those galaxies?
They're stars and galaxies, looking through everything. A lot of these will be galaxies because this is perpendicular to the galactic plane. Later, it'll show a galactic plane view.
Amazing.
And it's going to do this 4 nights later and see if there's any change in any of these things. Well, that is a big question. I'll talk about that in a minute. Question was, who's going to read all that data? Okay, now here's in our galaxy, just our galaxy, the Laguna area, and you see all the stars. Remember, our galaxy has 200 billion stars, and maybe from here you can get an idea of how 200 billion is really a big number.
Colors realistic?
Well, they're realistic in the sense of it's the best idea of what you might see if you were floating around in space there. Okay. But it's probably you wouldn't see anything if you were out in space there, but pretty good idea. These dark clouds. And when you see areas where there are fewer stars, It's not that there are fewer stars, but there are these clouds in front of them. See, here's a lot of stars. And this is just the start. They have spent the first. Finish this off. Okay, things that it's going to do. It's going to image the entire southern sky every 3 or 4 nights. It's expected to give 7 million alerts of changes every time. And they just did a test. They're still running tests. They did the first test to see if they could see if things were changing. And the first night they did it, they found 800,000 objects that had changed their brightness. That's just the testing they're doing. They're going to be looking at about 20 billion galaxies over the 10 years for the project. They'll monitor 10 million quasars. It's going to probably find about 1 million supernovae in those 10 years. I think so far we've found about 500 supernovae. That number quite a bit. It's 2 billion pixels camera, biggest camera ever built. And it's going to get, whatever this means to you, 20 terabytes of data every night. I think your iPhone has about 1/3 of a terabyte of data in it. So, but so anyway, and so the question was, who's going to read all this? It's very clear that a very major challenge, and they've always realized this, of this project is going to be, how do you deal with these huge masses of data? So there's very sophisticated computer programming. I'm not familiar with them very much. Artificial intelligence is really getting in. You know, how are we going to identify this? What's interesting? What's not interesting? And so on. So this is a major challenge, but change everything. Okay, this is it's named for Vera Rubin. She was a very prolific astronomer. She did a very great deal with. Remember when I talked about dark matter a little bit in a previous course? Dark matter was first hypothesized by Zwicky and Knacke, mainly Fritz Zwicky in the 1930s. But Vera Rubin in the 1970s showed that there was dark matter in our galaxy. By measuring the motion of stars in the galaxy, she was able to show that there was lots of dark matter in our galaxy, and that was determining, for example, how fast the sun is going to the center of our galaxy. And he worked with Kent Ford. He doesn't seem to get a lot of credit for it, but it was a very close collaboration. He built all the instrumentation that she used. So she passed away about 2 years ago. Might be interesting to do about her and her career, the way Barry Bowen does lectures, you know.
How did they come up with that that dark matter exists? Is that
well, the original, okay, question is, how do we know that dark matter exists? That was your question?
Yeah.
Or I'll have to do this very briefly, though. Zwicky's original measurement was, he looked at clusters of galaxies, saw pictures of galaxies. He looked at clusters, and they were like, you know, a bunch of mosquitoes all flying around in a big swarm. And the galaxies are all attracted to each other. But then when he measured the gravitational force of those galaxies, there wasn't enough gravity there to hold them together. It would all fly apart. And yet here were these ancient clusters. So he said there has to be matter there that we're not seeing. And Vera Rubin did kind of what you suggested. She looked at the speed things orbiting, you know, that we have this big pinwheel thing and it's orbiting. So look at the speed of stars orbiting, like our star, our sun, how fast it's orbiting. And from that, you can calculate what it takes. You know, we can calculate the mass of the sun by how fast the Earth orbits. And it didn't come out right. You needed 6 times more matter than the stars had.
Even in our solar system?
Not in our galaxy. Okay, in our galaxy. And so that proved that there has to be dark matter. Okay, so that I can't do a whole lot more detail. It's a whole course. So. All right. All right. Okay, now let me talk. Yeah, I'm a little short on time, so I'm going to have to figure something out. All right, here is something that the James Webb Telescope discovered. When we first got the first images from the James Webb Telescope, the first one was awesome, beautiful, etc. But it was kind of in a way what people expected. See lots of galaxies, see lots of some nearby stars. So lots of these big diffraction spikes are nearby stars, but we look past those and look at extremely distant objects. But then, when we look more closely, there were these funny little red things. And when we looked at those more carefully, they turned out to be very massive objects. You know, 50, 100 solar 100 million solar masses, and very far away. And they are very, when you look at the, you know, the James Webb Telescope looks at very distant objects, and that's very early in time. And these things were very abundant around when the universe was 500 million years old. And now we're getting some when the universe was just 300 or even 200 million years old. And they're all over the place. And then, but they disappear after the universe is about 1.5 billion years old. Beyond that, we don't see them. And here's another one, 13.5 billion light years away. Pretty small, 1,600 light years compared to a regular galaxy. And here's a whole bunch of them. They're everywhere. And this 2 years ago, this was very confusing. There were these little red things. There were way too many of them. They were way too far away. They were way too bright, and we couldn't understand them. So it's something really new that James Webb has discovered. And so they were now called the little red dots, LRDs. And well, if you could look closer, you'd see this. It's full of little red dots all over the place. So, and here I just size of one of these, if it were compared to the size of a regular galaxy. So they're very small, but they're extremely massive. You know, 100 million solar masses, extremely bright. And here's some more. Let's see what it, I can't remember why. Let me pass that. Yeah, the other thing is, this is a kind of a little red dot. They're not all the same. They all vary. But one of the things you can find about them, they're very early in the universe, but we can identify some of what they're made of. And it's not surprising there's lots of hydrogen in them, because the early universe was full of hydrogen. So there's helium, but they also have neon and oxygen. This one has neon and oxygen. There are elements as well. And we know that those are typically made in stars. But here, very early in the universe, a few 100 million years old, we already have these elements. So there must already have been an epoch of star formation or events of stars before this to get these galaxies rich in these heavy elements. So here's just this is a few things that I'm worried about. This is this one, USO1, is 700 million years in the universe. pretty small, couple hundred light years. That's a mass of 10 to the 50 million light years. It's unlikely to have formed from a soup. The host galaxy is poor in metals, suggesting it's unlikely to have formed from a supernova. It's unlikely to have been just grown by accretion. That's one of the things we don't understand. If it's 50 million solar masses, how could it grow so fast in just a couple hundred million years? So one of the ideas is that is now being investigated directly is that it's something called a direct collapse black hole. Remember, the way we made black holes in our galaxy today is the end states of stars. Stars get old, they explode, what's left is a black hole. That's confirmed. But that couldn't have worked in the early universe. Didn't have time to go through all that evolution and stuff and then grow. So what the idea is, there must be another way to make black holes, and maybe the black holes are formed by direct collapse of interstellar clouds, of early clouds. So we have bright galaxies at very early times, and we have very early supermassive black holes. These red dots have black holes which are in the order of 100,000 to 10 million times the mass of the sun, or even greater. And there was a paper came out in January which showed that it made the black hole a little bit smaller, but it showed a very consistent interpretation that now looks very strong that we are seeing black holes in these red dots, and that's what's powering them. But they're not like what we know, because ours are in much bigger galaxies. The red dots have little X-ray emission and don't seem to be too variable, but that's still studied. So they may be a new kind of object, a dense small gas cloud object powered by black holes. That's the idea that people are looking at the most right now. So here's how it might form. This is our suppression. We have a big early cloud. Cloud starts, this is the center of it. Cloud starts condensing, but as it condenses, it forms a black hole, which isn't what's happening in the universe today. And then that left with a big black hole at the very start. And it might be something like this, now called a black hole star, that you have a black hole in the center of this object, and this is bounded by ionized matter, clouds, and instead of this sort of star-like object, instead of nuclear reactions powering it, there's this central black hole which is gobbling up matter like crazy, and then powering this whole gas cloud around it. And that idea has some merit. It's been studied theoretically. So it surprised everyone that in a direct collapse like this, mathematically, there's a suggestion that the black hole can form, but it will leave a lot of this matter around it. And then when the black hole starts accreting matter, putting out a lot of energy, it illuminates this thing, turns it red dot. But that's what we may be seeing. And this may be how galaxies started. Okay, so yeah. Yeah. Okay.
Yeah, is there evidence for the dense cloud?
Yes, yeah. We see the gas, and we can get spectra of it. It's the reddish color. It's red for two reasons. One is it's just very far away, and then things get red because of the expansion of the universe. But it's also intrinsically red. Okay. And the other thing is we can see how light gets scattered. There's this paper in January, which I think tells a lot. It looks at how light is scattered by electrons in a big cloud. And that has certain properties and appearances, and they match that with the red dots. So that looks like it's something really worth pursuing. Okay, so I'm going to leave it here. What we think is happening, the red dots may be the first galaxies, maybe are certainly an important thing in galaxy evolution. And then over the next 13.8 billion years, things evolve, galaxies collide, things change, and eventually we end up things like this with Andromeda. But this is now a major area of research. How do galaxies form and how do they evolve and change into what we see? And I don't pretend to have the answer. Okay. What, can I go backwards here? Yeah. Okay, let's take a break. Everybody? Hey, shut up. Okay, well, if you thought the first part of this was wild, you haven't seen anything yet. This is gonna get really weird. Pretty soon. Okay, so I'm just gonna talk about three different areas that are big in astronomy right now, and that they're more far out than I thought, than we mentioned before. One thing, I'll get back to gravitational waves a little bit, because I think this is a very interesting project. Remember, we talked about LIGO and how it found the gravitational waves, and it found these whole mergers with LIGO. And remember, those events took place in fractions of a second. So they're very high frequency events. The frequency is just the inverse of the time. So they happen very quickly. Talked about LISA, which is going to be in space and going to measure the distance change as a black hole comes through about a 2 million kilometer length. And that will be able to determine lower frequency events. Maybe another way to look at it is that the wavelength is related to the frequency. The wavelength of the event is roughly the size of the instrument. And then now the third one, and this is one I want to discuss a little bit, is called the pulsar timing array. And this will be a different system. We'll look for even lower frequency events. And see, these were merging small black holes, 50, 30, 20, 50 solar masses. This will look supermassive black holes. This will look for even bigger black hole collisions. And the way this works, is this, that we remember pulsars, that we talked about pulsars, regular pulsing stars. Well, they pulsate so regularly, they're like a clock. And so if we get a pulsar and we suddenly see it changes, that may mean that the space was stretched a little bit by a gravitational wave. And we could then determine that a gravitational wave had passed, but over a distance of many light years, so a huge distance. And it shows several pulsars and so on. And we have an array now that's looking for this effect. There are lots of other reasons that the pulses can change. Sometimes the neutron stars, which cause the pulse, click a little bit or have a glitch, but we can work around all that. So here's the Crab Nebula, and remember that these pulsars are product of these supernova explosions, and the remnant in the center, again, the crab in a different color. The remnant star is a neutron star in the middle, and it pulsates. You can see in time here how it gets brighter, and this does it in 33 times a second. So imagine a neutron star is something like the mass of the sun. It's 10 kilometers across, and it rotates 33 times a second. Imagine that. So, yes. So here is 30 times a second. This, I've just simulated this. You can see, you can barely see with your naked eye, a pulsation that fast. The next one I have, I slowed it down to 15. Now you can really see it. Okay. Because, this is fun because both Walter Bade, who worked on supernovae, and Rudolf Minkowski, who I knew as a grad student, they both had looked at the central star of the Crab Nebula, realizing it was the remnant of the supernova. And they looked at it with the naked eye in those days.
Oh.
See, and if it had been a little bit slower, they would have seen it pulse with the naked eye. If it had been 15 instead of 30, they would have seen it. And Rudolph said, well, I didn't see it. It's too fast, and so, but he had the right idea, he would almost have done it. That's fun. Anyway, so that's the deal. The pulsars at all different speeds and so on. All that has to be worked out together. And we've got this big array of telescopes all over the Earth. Some in Africa, Europe, North American nanos, the Indian pulsar timing array, and South Africa, Australia Parkes pulsar array. So these are some of the telescopes that are working on this project. I think this one is the Atherton one. This is the Green Bank radio telescope in Virginia. This is a telescope in Germany. And this, I think, this one is the Australian one. Okay, so what are they doing? All right. Well, they have some initial results after 10 years of work. And this is the result, and it's kind of complicated to explain what's measured here. But let me just say what they're looking for. It would be great if they found two supermassive black holes colliding. That's all that meant. But what's more likely, and what they're looking for, at least initially, is that there's been supermassive black holes colliding ever since the universe began. And so there's a background, random things going in every directions. And detecting that is something it would tell us about supermassive black holes. And this correlation is a little bit hard to understand, but if they were finding this background, it would follow the dotted line, the black dashed line. And I think you can kind of see the observations are the blue points, and the uncertainty, how uncertain they are, is measured by the length. Okay, and now you can kind of see it kind of fits, but it's not totally convincing, right? We need to have better what we call signal to noise ratio here. So they have announced that they say we have an indication, but we cannot yet claim an observation. So that's where that stands. It's a huge effort to do this, but it's very hopeful that they may come up with something. So let me mention this background idea. What is a background? See, this slide. Wait a minute. Okay, see, normal waves that you see, they have a definite specific. We know they come from Alaska and stuff. There's storms up there and so on. Some are even named after mavericks and so on. So they have a specific thing. That's like two things colliding. But in addition to that, the ocean also. It's not doing it. Come on. There. In addition to the waves, there's also this random stuff here, right? And you know that some of it's due to wind, some of it's due to leftover waves, some of it's due to an otter jumping into the water, and whatever. But it's the background. And the background tells us something about what's going on. And that's what they're measuring now with the pulsar timing array. a background of gravitational waves. And I was at a conference in December. It was an excuse. I had to prepare for this class, so I had a good excuse. And he argued that what is seen with the pulsar timing array so far is at least consistent with a background of supermassive black holes. Again, it's not definite yet, but it's consistent. So I'm telling you where we are on this stuff. And you know, it's not easy. We started working for many years.
How do you differentiate between that background and say the background from the Big Bang, which they discovered with radio telescopes?
Well, but that doesn't influence the way pulsars fluctuate.
It's measuring a different background.
Yes, different background. Okay, so well, it's this graph again, and so we're measuring the solar mass black holes with this instrument, measure galaxies, collisions, and so on with LISA and with PTA, hopefully. And this would be another region to explore. Yeah. The H, that's the strain. Strain is defined as if you stretch a rod and it stretches a little bit, you divide the amount it stretches by its original size. That's strain. And it measures the strain. If you know, this is 2.5 kilometers long, then the strain here is a part of 10 to the 20th. So it's 10 to the minus 20 of 2.5 kilometers. That turns out to be less than the size of a proton. It's very, very small. But one of the good things about these difficult measurements here, though, is that in fact the strains are bigger. So nature is being nicer. That makes it slightly easier, even though measuring it at lower frequencies is hard. But the strain gets bigger. Okay, now another topic. This is Hawking radiation. And it's by Stephen Hawking. He did this. And let me explain it for the background. It turns out, yeah, the vacuum is not so empty and black holes aren't so black. Something. And what was known before Hawking did this was that imagine vacuum. Now I'm talking about nothing in there. There's no gas molecules, there's no magnetic fields, there's no electrical fields, no light, nothing. Pure vacuum, empty. Not quite. Because quantum mechanics tells us that what can happen in the vacuum, what does happen in the vacuum, is that you get instantaneous creation of particle pairs. Things like electrons and anti-electrons, protons and antiprotons, for just moments. Here's the creation. The two appear, and then a tiny fraction of a second later, they annihilate each other and disappear again. And this goes on all the time in the vacuum. Vacuum's buzzing all of this stuff. That's something that quantum mechanics calculates. That you never have this exact certainty of anything, and you don't have exact certainty of nothing in the vacuum. It fluctuates a little bit.
Is that
Now,
an
this,
energy neutral thing?
well, that's one of the good ways to look at it. There's two ways to look at it, to my mind, anyway, how I look at it. When a particle pair like this is created, it's an antiparticle and a particle, and they both have energy. Where does the energy come from? You know, we're told since the 5th grade that energy is conserved or something. Well, there's two ways to look at that. The way Hawking describes it, and by the way, I took this image from a paper of Hawking's, is that one of them has negative energy. The other has positive energy, so it's zero. But what's negative energy? Well, he doesn't explain that. As far as I can, I think it's real, but as far as I can see, there's no classical analog to it. It's strictly a quantum mechanics concept. There's nothing in our ordinary life that's similar to it. It's one of those quantum mechanical things that you have to kind of accept. that it's different from our world. That's one way to look at it. The other way that I like to look at it is that there's an uncertainty relationship between energy and time. We can never measure energy, either of those two things super precisely. The more better we measure energy, the less well we can measure time. The more accurately we measure the time something happens, the more uncertain its energy is. And so all happens within a time uncertainty. And so we're allowed to maybe violate conservation of energy for a very brief, uncertain period of time, because that's also uncertain. Don't understand that myself.
So we have matter in our universe. Is there some speculation about the matter, antimatter early in time?
Yeah, that's a whole nother topic. One of the unknown questions in the science today is, since we have since we have two types of matter, matter and antimatter, why is the universe only matter?
Yeah.
What happened to it? But I can't go. It's an interesting subject, but I suggest you artificial intelligence with it, okay? Because I didn't have time to get to it. Yeah.
Have there been experiments to quantify it?
Yes.
I imagine you can create a vacuum in the lab and insert some kind of energy detection apparatus. Is that something you can do?
Yes, it has exactly what you say. I'll get to that in a second. I tried to make an animation to illustrate that and see. It creates and then it disappears and another one appears somewhere else. And so I don't know if it's going to do it. It is doing it, and then it disappears. Well, I don't know how impressive that was. That's what's supposed to happen, except a lot faster than what I did. Okay, and now to your question, Doug. The fact is, it has been measured because when you use the same vacuum here, but if there's a hydrogen atom nearby, then the effect of these fluctuating fields that these create affects the lowest orbit of the hydrogen atom. And that's called the Lamb-sheet, and it was measured in 1947. And it shifts the energy levels of the hydrogen by a small amount, but a measurable amount, and it works exactly out right. So it's a real effect, not something invented. Well, we can never make a perfect vacuum where we are. It's just if there's a in this room, it will have its lower bounds energy levels change a little bit by the virtual particles that are in this room at the same time.
Oh, I see.
Okay. Yeah, I kind of emphasize vacuum, but it happens even when there's no vacuum. These virtual particles are happening all the time. Happening in your brain. All right. Now here's what Hawking said. This is also from Hawking's paper. That what can happen here when you're near a black hole. This looks like a black column, but in fact, he's measuring space this way and time this way. Okay, so what happens when a virtual particle pair is created, one of them can go into the black hole, and one of them can leave, become a regular particle that we see. And the way this works is that when this particle falls into the black hole, you'd think it would add mass to it, but in fact, it takes mass from it when it falls in because that's its negative energy. And this one has positive energy, we could see it. And so Hawking proposed that and showed in 1974, I think this was, that black holes evaporate. They can evaporate by this process, by the fact that when a virtual pair is near the extreme gravity at the edge of a black hole, that can disrupt the virtual particle and they don't recombine. But one goes into the black hole, one goes out to us. And that's called Hawking radiation. And so here's just another picture of how to look at it. You have this black hole, and near the Schwarzschild radius, you have one of them going in and one of them going out. Well, this is kind of neat. It's never been observed. But the thing you can be good about is that this is an extremely slow process of evaporation. Because a solar mass black hole takes 10 to the 7 years to evaporate. And the universe is only 10 to the 10 years old. So, we don't have to worry too much about that. But it turns out smaller ones evaporate faster. And so you can calculate that if there was a tiny black hole, if they exist, which has the mass of Mount Everest, then it would just now evaporate.
Because it's random, wouldn't there always be a relative equality between the number of negative particles that are absorbed by the black hole and the positive one escape, and vice versa? That half the time it would be the positive particle.
Yeah,
that goes in the
that's right.
black hole.
It's a neutral, you get neutrons, protons, negative protons, electrons, positive electrons, everything, and light, all would escape by.
But what I'm saying is that there would be balance. You have only evaporation because there'd be a majority of negative particles going in the black hole.
Yeah, negative, okay. The way you're saying it, I thought you meant negatively charged, electrically charged. That's balanced out completely. But I'm talking about negative energy, which is different from negative charge. And the negative charge, the negative energy ones fall into the black hole and take energy away from the black hole in that regard. So energy is conserved. The black hole gets smaller, we have radiation outside. Now, anyway, none of this is ever, but it probably does happen. But the neat thing about this, the important thing about it, I think, is this, that what Hawking did, he wasn't quite the only one, but he was really the leader in this, or a leader, is that what's is that he has taken a calculation which combines the extreme gravity that we derive from general relativity. A general relativist and a quantum mechanical event. And he calculated in an approximate way what would happen. And it's been a goal of science for many years because we have this great general relativity, the very big, and this great theory of quantum mechanics, the very small, and they don't go together. And the goal of science for many years, not complete at all yet, not even very far along, has been to combine those. We ought to have one theory of nature. Right? So that's something people. Yes, it conserves energy. When you go into the tiny details, you get moments when it's not, but overall it's conserving energy.
There was a suggestion that negative energy is more likely to go into a black hole.
Yeah.
In order for it to be evaporated.
Yeah, yeah.
Is that true? I mean,
That's what he calculates.
that's what he.
You gotta understand, I think the way Hawking pointed this, the way this works is these are quantum mechanical calculations. So we really believe in this theory. The problem with quantum mechanics is not that it's wrong. It's been right every single time, ever since 1925 when it was written down. No contradictions ever. What's the difficulty with it is for us to understand it, for us to picture it. That's always the tricky thing. And Richard Feynman, I think, discussed this very well. And he said, don't keep looking at quantum mechanics as something weird, you can't understand it, and it's so paradoxical and so on. You never get out of that mode. That just believe this is how nature works, and we've got to try to understand how nature works. The paradox, to my mind, is not so much how strange quantum mechanics is. The paradox is, why is it so hard for us to understand something that nature is all the time? Okay? Let's go on to something a little more weird than that. These are wormholes.
Very weird.
You've probably heard of these before. And the idea of this is actually a solution to which Einstein, I think, first came out with, that people are working on, is that there is a solution. There are relativity, that you can have a region of space which is connected directly to another region of space without you having to travel on the. It's somehow connected to another part of space. It's one of those predictions of general relativity, never been seen. But you know, black holes were a prediction, and people had a hard time believing it. So so if there is this kind of connection, people always wonder, can we travel through? In the movies, and people have all said, but you know, it's so hard to travel otherwise. It takes millions of years and so on. So black holes is really, I mean, these wormholes really be a cool thing to do. So it may not be so easy though. First of all, no one knows if they form, but the calculations themselves say these wormholes are very unstable. They don't last very long. And worse than, if you put a mass into the black hole, that makes it even more, into the wormhole, I keep saying black hole, wormhole, that makes it even more unstable. Because its gravity is pulling on it. So, so this seems to make it that it's not possible to travel through a wormhole. But people are still trying to look ways it could work. So I don't know. All right, so this is the problem. If you were trying to get into a wormhole, whoops, I wrecked the whole thing. This is what would happen. It would pinch off. Okay. Yeah, let me show that again, but I worked so hard on this and now I wrecked it. So I think it's probably good to remember, if you do see a wormhole, it's probably not a good idea to get into it. All right.
So is there any way that currently, maybe you're getting that, because there must be energy that goes through there to see that this is happening, and you still find that at some point?
Well, I would suggest there's a good discussion of things like this. One thing that kind of annoys me is that the negative energy comes back again. If someone said, well, there's no energy to the wormhole, maybe that would stabilize it. Okay. Okay. There something like that has ever been seen. They're unstable, and people are still looking at it. And if you want to learn a little bit more about this, the difficulty like this, people get ideas, you know, what if Superman flew through it, you know. But this is a serious book by Kip Thorne, and might really be interested in that, more about stuff like this. Okay. Well, it's really been fun. Thanks for coming, and thanks for asking. Thanks for all asking these questions. And what's personal note, what's fun for me is that this is a way for me to organize my thinking and getting caught up more in a field that I wasn't actually